On July 14th, 2015, a photograph arrived at a laboratory in Maryland after traveling for more than 4 hours at the speed of light. The image showed something no one expected to find on Pluto: a bright, smooth, heart shaped region stretching across the surface of a world that every major model had predicted should be frozen, ancient, and geologically dead. But it was not the heart that changed everything, it was what appeared to be hiding beneath it. Evidence began pointing toward an ocean of liquid water buried deep below Pluto's icy crust. An ocean on a world where surface temperatures fall to roughly minus 230 degrees Celsius. A world so distant that the sun looks more like a brilliant star than a source of warmth. And the deeper scientists looked, the stranger the picture became. This hidden ocean may be denser than Earth's seawater. It may have existed for billions of years. No sunlight has ever touched it. And somehow, on one of the coldest worlds in the solar system, something has prevented it from freezing solid. The spacecraft that uncovered the mystery carried something else as well: a small container holding the ashes of Clyde Tombaugh, the astronomer who discovered Pluto decades earlier. What began as a mission to photograph a distant dwarf planet became a challenge to everything scientists thought they understood about where oceans can survive. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. The story begins with a world that spent most of its history dismissed as a frozen relic at the edge of the solar system. The story begins far from icy plains and buried oceans. It begins with a young man leaning over a machine in northern Arizona. On February 18th, 1930, Clyde Tombaugh sat at a blink comparator inside the Lowell Observatory in Flagstaff. A blink comparator was a device that rapidly alternated between two photographs of the same region of sky, allowing moving objects to stand out against fixed stars. Tombaugh was only 24 years old. He had no university degree. No formal path had carried him there. Back in Burdett, Kansas, he had built telescopes from used tractor parts and automobile components. At night, he sketched Mars and Jupiter by hand, filling page after page with careful observations. Those drawings eventually reached the observatory's director. The quality of the work was impossible to ignore. A job offer followed, and with it came a difficult assignment. The observatory was searching for a hypothetical world known as Planet X. Percival Lowell had proposed its existence years earlier while attempting to explain apparent irregularities in the motions of Uranus and Neptune. Whether the prediction was correct remained uncertain. The search itself was painstaking. Night after night, photographs captured the same patch of sky. Days later, Tombaugh compared the glass plates through the blink comparator. Most points of light remained fixed. Stars held their positions, but anything that shifted between exposures demanded attention. Then came a small movement. That afternoon, while examining images taken in the constellation Gemini, Tombaugh noticed a tiny dot displaced by roughly 3 millimeters between photographs. The shift was subtle, yet it was enough. A new world had revealed itself. Confirmation followed, and on March 13th, 1930, the discovery was announced to the world. The object soon received a name suggested by an 11-year-old English schoolgirl, Venetia Burney. She proposed Pluto, the Roman god associated with the cold underworld. The choice carried another layer of meaning. The initials P and L also honored Percival Lowell. For the next 76 years, Pluto occupied a familiar place in textbooks as the ninth planet. Generations grew up memorizing its name. Then, on August 24th, 2006, the International Astronomical Union voted to reclassify Pluto as a dwarf planet. The decision sparked arguments that still linger today. Tombaugh never witnessed the debate. He had died in 1997. Yet the same year Pluto lost its planetary status, another chapter quietly began. NASA launched New Horizons toward the distant world. Tucked inside the spacecraft was a small aluminum canister containing 30 grams of Tombaugh's cremated ashes. As the probe crossed the vast darkness beyond Neptune, the man who discovered Pluto traveled with it. 9.5 years later, New Horizons arrived. The findings that followed transformed Pluto from a forgotten outpost into one of the most astonishing worlds ever explored, making its demotion feel like one of planetary science's greatest misjudgments. Most spacecraft spend their lives fighting distance. New Horizons treated distance like an obstacle to be outrun. On January 19th, 2006, an Atlas V rocket lifted away from Cape Canaveral, carrying a probe built for a destination nearly 5 billion kilometers from Earth. The moment it escaped our planet, it entered the record books. Its departure speed reached roughly 58,000 kilometers per hour, faster than any spacecraft had ever left Earth before. The pace was relentless. Just 9 hours after launch, New Horizons crossed the orbit of the Moon. Apollo astronauts needed about 3 days to cover the same distance. Earth was already shrinking behind it. Yet even that velocity was not enough. 13 months later, the spacecraft arrived at Jupiter. There it performed a gravity assist, a maneuver that uses a planet's motion and gravity to increase speed. Think of it as borrowing momentum from a moving world. The encounter added roughly 14,000 kilometers per hour, sending the probe deeper into the outer solar system. Then came a different phase. For much of the next 9.5 years, New Horizons slept. Engineers placed the spacecraft into long periods of hibernation to reduce wear on its systems and conserve resources. Every so often, it awakened for instrument tests, health checks, and small trajectory adjustments. Then it returned to dormancy and continued its journey through the darkness. The spacecraft itself was remarkably compact. Its mass was about 478 kilograms. Power came from a single radioisotope thermoelectric generator, a device that converts heat from radioactive decay into electricity. Inside was plutonium 238, producing roughly 200 watts of power, less than many household appliances. That modest supply would support the entire mission. Among its instruments was the Long Range Reconnaissance Imager, usually called LORI. This camera could resolve details on Pluto as small as a football field. Across billions of kilometers, it would become our sharpest eye. Communication remained a challenge. From Pluto's distance, data returned at roughly 1 to 2 kilobits per second, by modern standards, painfully slow. A single image could require hours to arrive. The complete scientific record would take 16 months to transmit home. At 11:49 Coordinated Universal Time on July 14th, 2015, New Horizons swept within 12,500 kilometers of Pluto's surface while traveling about 50,000 kilometers per hour. You could not circle Pluto at that speed. There was no fuel to break, no opportunity to try again. Everything depended on one pass. Roughly 30 hours of observations were packed into a window narrower than a single day. Later that evening, a sequence of status messages began its 4.5 hour trip back to Earth. When they arrived, every major objective had been completed. 236 scientific observations, 7 instruments, 6 known worlds in the Pluto system. The data would trickle home for more than a year, but the first images arrived within days, and they revealed a place that looked nothing like anyone had expected. Imagine opening a package from the edge of the solar system and discovering that almost every expectation inside was wrong. As the first detailed photographs streamed home from New Horizons, Pluto began shedding its old identity. For decades, textbooks had portrayed it as a frozen relic, a small and inactive world lingering beyond Neptune. Yet the images revealed mountain ranges, sprawling plains, layered atmospheric hazes, and landscapes shaped by ongoing processes. You were no longer looking at a simple ball of ice. One feature stood above all others, stretching across roughly 1,600 kilometers, was a brilliant heart-shaped region, later named Tombaugh Regio, honoring the man who first found Pluto. Against the darker terrain surrounding it, the formation was impossible to miss. It quickly became the symbol of the mission, but scientists soon realized the most important story was hidden inside the heart itself. Its western half carried the name Sputnik Planitia, after the first artificial satellite launched from Earth. Here the terrain dropped several kilometers below the surrounding landscape, forming an immense basin approximately 1,200 kilometers wide and 2,000 kilometers long. Together, its dimensions rivaled the combined area of Texas and California. The basin was not empty. Instead, it held vast deposits of frozen nitrogen mixed with methane and carbon monoxide ice. Nitrogen dominated the landscape. Under Pluto's conditions, these materials behave very differently from familiar rock and soil. They can flow, shift, and reshape the surface over immense spans of time. Then another surprise emerged. Sputnik Planitia contained remarkably few impact craters. Across the solar system, craters serve as clocks. The more impacts a surface accumulates, the older it generally is. Yet large portions of this basin appeared astonishingly young. Some regions may have formed only a few 100,000 years ago. That is an eye blink in planetary history. Pluto is approximately 4.5 billion years old. A surface lacking craters on such an ancient world immediately signals activity. Something had been erasing the scars left by incoming objects. Something was renewing the landscape again and again. But the deeper puzzle involved location rather than appearance. Sputnik Planitia sits close to Pluto's equator and almost directly opposite the hemisphere that permanently faces Charon, its largest moon. Planetary scientists examined this arrangement carefully. If the basin were simply an enormous impact crater, it would represent a mass deficit, meaning a region with less material than its surroundings. Physics predicts a different outcome in that case, through a process called true polar wander, which means a world slowly reorienting itself to achieve a more stable rotation. Such a feature would tend to migrate toward the poles. Sputnik Planitia did not. It remained locked near the equator. Even more strangely, it behaved as though extra mass existed there rather than missing mass. The gravitational signature pointed downward and inward towards something dense. Far beneath the frozen nitrogen plains, something heavy was pushing upward from below. The simplest explanation was also the most astonishing. The models that described Pluto as geologically dead had failed. Beneath its frozen heart lay liquid water, an ocean. Scale can be deceptive in the outer solar system. Some worlds appear immense in our imagination simply because they are distant. Pluto is not one of them. Its diameter measures just 2,377 kilometers, making it smaller than Earth's moon. If you could place it across parts of a continent, it would feel surprisingly modest. Yet hidden inside this small body is a problem that planetary science still wrestles with today. Consider where Pluto lives. It circles the Sun at an average distance of roughly 5.9 billion kilometers, about 39 times farther out than Earth. From that remote vantage point, the Sun no longer dominates the sky. To you, standing on Pluto's surface, it would resemble an exceptionally bright star rather than the large glowing disk we know. The available energy is tiny. Pluto receives only about 1/1600th of the sunlight reaching Earth. Surface temperatures hover near negative 230 degrees Celsius, or about 40 Kelvin. A Kelvin is a temperature scale used by scientists, where zero marks the complete absence of thermal energy. By almost any standard, Pluto is a profoundly cold place. Before New Horizons arrived, computer models painted a straightforward picture. Any liquid water created during Pluto's early history should have frozen solid within a few 100 million years. Small worlds cool rapidly. They possess limited internal heat and relatively large surface areas through which that heat escapes. Pluto seemed destined for that fate. Unlike Europa, it has no giant planet constantly flexing its interior through tidal heating, which means heat generated by gravitational squeezing. Unlike Enceladus, it is not being stretched and compressed by Saturn. It drifts alone through the darkness. The calculations appeared convincing. The mathematics said no. The physics said no. Decades of thermal evolution models, which are simulations tracking how worlds cool over time, also said no. But the evidence arriving from Pluto pointed elsewhere. Several independent clues began converging toward the same conclusion. One came from the unusual gravity signature associated with Sputnik Planitia. The basin behaved as though dense material existed beneath it, consistent with liquid water pushing upward from deeper layers. Another clue stretched across the surface itself. Scientists identified extensional tectonic features, meaning fractures formed as a world expands. Long cracks and troughs, known as graben, crossed portions of Pluto's crust. These structures suggested gradual outward growth over immense spans of time. Such expansion fits a scenario where an internal ocean slowly freezes and increases in volume. The ice shell offered another piece of the puzzle. Estimates indicated a crust roughly 45 to 70 kilometers thick across much of Pluto, yet noticeably thinner beneath Sputnik Planitia. The variations implied a more dynamic interior than expected. Then, in 2020, researchers publishing in Nature Geoscience proposed a striking possibility. Pluto may have experienced a hot start, meaning a liquid ocean existed almost from the moment the dwarf planet formed, roughly 4.5 billion years ago. The implication was extraordinary. The ocean was not a late arrival. It did not emerge after some rare event. It may have been there from the beginning and persisted ever since. That realization leaves us with a deeper mystery. How does liquid water survive for 4.5 billion years on a world this cold, this small, and this far from everything? Some solutions in science arrive through enormous machines, decades of observation, or entirely new instruments. Others begin with a surprisingly simple question. What if the heat was never escaping in the first place? In 2019, a team led by Shunichi Kamada at Hokkaido University proposed an explanation that reshaped the discussion surrounding Pluto's hidden ocean. The idea did not require an unknown energy source. It did not demand exotic physics. Instead, it focused on insulation. Deep beneath Pluto's frozen crust, the researchers suggested a thin layer of gas hydrates, more specifically, methane clathrate hydrates. The name sounds complicated. The structure is easier to picture. Imagine countless water molecules arranging themselves into tiny cages. Inside each cage sits a methane molecule. Methane is a simple gas made from one carbon atom and four hydrogen atoms. Locked together under the right pressure and temperature, the water and methane form a crystalline material that resembles ice. But it behaves differently. Methane clathrate is exceptionally poor at conducting heat. Energy moves through it very slowly. That characteristic turned out to be crucial. According to Kamada's team, This layer sits between Pluto's liquid ocean and the solid ice shell above it. In effect, it acts like a thermal blanket. Warmth rising from below encounters a barrier that resists heat transfer. The ocean retains its energy, while the ice above remains cold and structurally strong. The concept could be tested. Researchers built computer simulations extending across roughly 4.6 billion years, nearly the entire history of the solar system. They ran multiple scenarios and compared the results. Without a clathrate layer, the outcome was straightforward. The subsurface ocean froze completely within a few 100 million years. Pluto eventually became exactly the frozen world earlier models predicted. With the insulating layer present, the story changed dramatically. The ocean remained largely liquid throughout planetary history. Even after billions of years, extensive water survived beneath the ice shell. Another result proved equally important. When the simulations excluded clathrates, a uniform ice crust developed over the ocean in about 1 million years. Uniform means roughly the same thickness everywhere, yet Pluto's crust is not uniform. Observations show significant variations across different regions. Including clathrates altered the timeline enormously. The formation of a fully uniform shell stretched beyond 1 billion years. That slow evolution matched the complex structure observed today. The theory also offered an origin for the methane itself. Within Pluto's rocky core, heat can break apart organic materials. As methane is released, it rises upward through the interior and becomes trapped at the boundary between ocean and ice, gradually forming clathrates. A separate puzzle suddenly became easier to understand. Pluto's atmosphere contains abundant nitrogen, but surprisingly little methane. If methane is being stored below as clathrates, its scarcity above makes sense. Nitrogen cannot be trapped the same way. It remains free to migrate toward the surface and atmosphere. The implications extended well beyond Pluto. Kamada noted that this mechanism could mean oceans are far more common than scientists once believed, increasing the number of places where conditions suitable for life might exist. The invisible blanket explained how the ocean endured. Yet the water itself possessed characteristics that were every bit as unusual as the mechanism preserving it. By the middle of 2024, researchers were no longer asking whether Pluto possessed an ocean. Attention had shifted toward a different challenge. What exactly was this ocean like? In May of that year, scientists Nguyen and McGovern, working through Washington University in St. Louis and the Lunar and Planetary Institute, published new findings in the journal Icarus. Rather than examining the water directly, they studied clues preserved in the landscape above it. Cracks, fractures, and subtle bulges surrounding Sputnik Planitia recorded the behavior of Pluto's interior over immense spans of time. The surface had become a map. By analyzing these geological patterns, the researchers were able to constrain, meaning narrow down, the physical properties of the hidden ocean below. Their conclusions painted a picture stranger than many expected. The water appears exceptionally dense. Their estimates suggest an ocean roughly 8% denser than seawater on Earth. For comparison, that places it in a range similar to the Great Salt Lake in Utah, where high concentrations of dissolved salts dramatically increase buoyancy. If you could somehow enter this distant ocean, floating would be effortless. Your body would ride high in the water, supported by its unusual density. Yet the reason for that buoyancy reveals something important. Pluto's ocean is likely saturated with dissolved minerals and salts accumulated over billions of years of interaction with the rocky material beneath. The scale is equally remarkable. Current estimates place the ocean's thickness between 40 and 80 kilometers. Even at the lower end of that range, the volume of liquid water would exceed that contained in any lake or sea on Earth's surface. Hidden beneath a frozen crust, an immense reservoir stretches around portions of Pluto's interior. Chemistry may also play a crucial role. Researchers suspect the water contains ammonia. Ammonia is a compound made from nitrogen and hydrogen, and it functions as a highly effective antifreeze. Even relatively small amounts can lower water's freezing point by many tens of degrees Celsius. In Pluto's environment, that property becomes extremely valuable. The ocean may therefore remain liquid at temperatures where pure water would become solid ice. Above it lies an ice shell estimated to be roughly 45 to 70 kilometers thick across much of the dwarf planet. Through all those kilometers of frozen material, no sunlight penetrates. No sunrise has ever occurred there. No beam of daylight has crossed those waters. The environment is unlike anything humans have experienced. No wind reaches it. Surface weather never disturbs it. Charon's gravitational influence becomes subtle at those depths, producing little tidal motion. What remains is dense, cold, mineral-rich water under immense pressure, occupying a realm no person has ever observed directly. Yet when scientists compare these conditions to certain places on Earth, familiar patterns emerge. Deep beneath Antarctic ice, below sea floors, and around chemically active environments, life persists without sunlight. Energy comes from chemistry rather than the sky. That similarity does not prove anything about Pluto. It simply expands the conversation. But the ocean is only part of the story, unfolding beneath the crust. Above it, the frozen surface itself is moving, slowly, visibly, and continuously reshaping the landscape. From high above Sputnik Planitia, the landscape resembles a vast patchwork stretching toward every horizon. Large geometric shapes cover the basin floor, outlined by shallow troughs and arranged in patterns unlike anything seen elsewhere in the solar system. New Horizons captured them in remarkable detail. Across the center of the basin, these polygonal cells average roughly 33 kilometers in width, though their sizes vary considerably. Some span only 10 kilometers, others approach 40. Together they create a surface that appears organized at first glance. Yet no two regions are exactly alike. Look more closely, and another detail emerges. The centers of many cells sit slightly higher than their boundaries. The difference is modest, around 50 meters in elevation, but enough to give each cell a broad, gentle dome. The effect is subtle. Entire landscapes rise and fall by the height of a modest building. These shapes are not frozen accidents. They are convection cells, visible expressions of a process called solid-state convection. Convection occurs when warmer material rises while cooler material sinks. We often associate it with liquids or gases, yet under the right conditions, even solid materials can flow. Nitrogen ice on Pluto happens to be one of them. Deep below the basin floor, heat from the interior moves upward through the layers above the ocean. As nitrogen ice near the bottom warms, it becomes slightly less dense. Over immense periods, it begins to rise. Upon reaching the upper layers, the ice spreads outward, cools, grows denser, and gradually sinks again near the cell boundaries. The cycle never truly stops. Movement is extraordinarily slow. Estimates suggest the nitrogen ice travels between roughly 6 and 18 centimeters per year. That is comparable to the rate at which a human fingernail grows. Yet geological time changes everything. At those speeds, the entire surface is eventually recycled. Scientists estimate turnover times ranging from roughly 500,000 years to 1 million years. Material rises, drifts, sinks, and returns below in a continuous circulation pattern. This explains a mystery that puzzled researchers from the beginning. Impact craters rarely survive here because the ground itself is constantly renewing. Any crater that forms is gradually softened, distorted, and erased as the ice continues its slow migration. The boundaries between cells tell part of that story. Some troughs reach depths of around 100 meters. Along these margins, darker material and blocky hills occasionally accumulate after being transported by the flow. The edges become gathering places where movement leaves visible traces. Conditions change near the perimeter of the basin. There, the polygons shrink and become more isolated. Instead of broad interconnected cells, scientists observe dome-like structures roughly 10 kilometers across. These smaller features mark locations where the nitrogen layer becomes thinner and convection weakens. A study published in Geophysical Research Letters during 2026 examined these marginal cells in detail. By measuring their dimensions, researchers were able to refine estimates of the nitrogen ice thickness across different regions of Sputnik Planitia. The result is a world whose frozen surface behaves less like stone and more like a living system of circulation. The ice above the ocean rises, spreads, sinks, and continuously rewrites the landscape. Yet, even this remarkable activity is only part of Pluto's story. Beyond the basin, the terrain records evidence of something even more dramatic. Along the southwestern edge of Sputnik Planitia, the terrain changes character once again. The broad cellular plains give way to something far larger and more imposing. Rising above the surrounding landscape are two immense structures that challenge our assumptions about what a frozen world should be capable of creating. They resemble volcanoes, yet they are unlike the volcanoes you know from Earth. The first is Right Mons, spanning roughly 150 kilometers across and rising between 4 and 5 kilometers above its surroundings. It ranks among the largest individual mountains on Pluto. Near its summit lies a vast central depression, approximately 56 kilometers wide. When planetary scientists calculated its overall volume, comparisons quickly emerged with Mauna Loa, Earth's largest shield volcano. Nearby stands an even larger giant. Picard Mons extends roughly 225 kilometers across and reaches heights approaching 7 kilometers. Current evidence suggests it may be the tallest cryovolcano ever identified anywhere in the solar system. The word cryovolcano requires a brief explanation. A cryovolcano is a volcano that erupts cold materials instead of molten rock. Rather than releasing lava composed of melted stone, it expels mixtures of water, ammonia, and other volatile substances capable of flowing under the right conditions. In a place as cold as Pluto, these materials play the role that magma plays on Earth. What makes Right Mons and Picard Mons especially intriguing is their apparent youth. Impact craters are largely absent from their surfaces. Across planetary geology, a low crater count generally indicates a relatively young landscape. These mountains may have remained active within the last few 100 million years, recent by geological standards. Their slopes preserve additional clues. Both structures display hummocky terrain, meaning landscapes covered with irregular hills and rough textures. Right Mons also features narrow ravines extending away from its summit region. Some researchers suspect these channels may have formed when liquid material once flowed downslope before freezing in place. Composition matters as well. Unlike the nitrogen rich plains nearby, these mountains consist primarily of water ice. At Pluto's temperatures, water ice behaves very differently from what you experience on Earth. It becomes extremely hard and rigid, with mechanical strength comparable to rock. The surrounding region, informally known as Hecho Palace, adds another layer to the mystery. Smaller mounds and scattered depressions appear throughout the area. Rather than representing isolated features, they hint at an extensive cryovolcanic province containing multiple eruption sites spread across the landscape. A study published in 2020 explored how such eruptions might occur. The proposed mechanism involves overpressure, which means pressure building beyond what surrounding materials can contain. If a pocket of ammonia rich liquid becomes trapped within Pluto's crust and begins freezing, its volume expands, pressure rises. Eventually, the enclosing chamber fractures, forcing liquid upward toward the surface. That possibility carries profound implications. Material originating deep within Pluto may occasionally find pathways to the exterior. The boundary between ocean and surface is therefore not necessarily complete. Connections may exist, linking the hidden interior to the world above. Convection beneath the plains, cryovolcanic mountains along their margins, an ocean persisting through billions of years. Pluto reveals itself as a place where internal processes continue shaping the surface. Yet, ice and water are only part of its story. Above the landscape drifts an atmosphere unlike any other in the solar system. One of Pluto's most extraordinary discoveries appeared only after New Horizons had already passed by. The spacecraft turned back toward the distant world and looked across its edge. There, illuminated from behind by the faraway sun, Pluto revealed a delicate halo surrounding its entire circumference. A thin blue glow traced the horizon, suspended above the frozen surface like a luminous veil. For many scientists, the image was astonishing. Mission investigator Alan Stern later remarked that few people would have expected a blue sky in the Kuiper Belt. Yet there it was, a world once dismissed as inert possessed, an atmosphere visible from billions of kilometers away. Its composition is deceptively simple. More than 99% consists of nitrogen. Small amounts of methane and carbon monoxide make up the remainder. At ground level, however, the atmosphere is extraordinarily tenuous. Surface pressure measures roughly 1 pascal, making it about 100,000 times thinner than Earth's atmosphere. Even so, it reaches remarkable heights. Before the flyby, models predicted a much lower haze layer. Instead, observations showed atmospheric material extending more than 200 kilometers above the surface. Some layers rose to altitudes nearly 5 times greater than expected. The structure proved surprisingly complex. Scientists identified more than a dozen distinct haze layers stacked above one another. These layers are created by particles known as tholins. Tholins are complex organic substances formed when sunlight alters simple atmospheric molecules and gradually assembles them into larger compounds. The process begins high overhead. Ultraviolet radiation from the sun breaks apart methane molecules drifting through Pluto's atmosphere. Those fragments react with one another and form increasingly complex hydrocarbons, including acetylene, ethylene, and ethane. Over time, they combine into tiny soot-like particles. Their effect is visible everywhere. Suspended in the atmosphere, these particles scatter blue wavelengths of light and create the characteristic haze observed by New Horizons. Eventually, they drift downward and settle onto the landscape below. Once deposited on the surface, they tint portions of Pluto with reddish and brownish hues. Another surprise soon emerged. Prior to the mission, researchers expected nitrogen gas to be escaping rapidly into space. Measurements revealed something very different. The actual escape rate was roughly 10,000 times lower than predicted. The haze itself appears to cool the upper atmosphere, reducing the energy available for atmospheric loss and helping retain Pluto's gases. But none of this is what makes Pluto unique. The truly remarkable feature lies in how its atmosphere behaves over time. Pluto requires 248 Earth years to complete a single orbit around the Sunday. Its path is also highly elliptical, meaning its distance from the Sun changes dramatically, ranging between roughly 4.4 billion and 7.4 billion kilometers. As Pluto travels outward and temperatures fall, the nitrogen atmosphere begins freezing onto the surface. Quite literally, an entire sky condenses into frost. Later, when conditions warm again, that frozen nitrogen sublimates, meaning it transforms directly from solid back into gas. The atmosphere collapses and rebuilds as part of a repeating planetary cycle. Longer rhythms operate as well. Pluto's axial tilt changes over approximately 2.8 million years, creating vast climatic shifts that redistribute nitrogen ice across the globe. Models suggest roughly 1 kilometer of nitrogen has vanished from the northern edge of Sputnik Planitia during the last 2 million years, balanced by fresh glacial flow arriving from elsewhere. Pluto has weather. It has seasons. It has atmospheric cycles operating across spans from decades to millions of years. Together, those processes have sculpted some of the most alien landscapes ever photographed. Near Pluto's equator lies a region called Tartarus Dorsa, and if you could fly low across it, the landscape would challenge almost every expectation you might carry about an icy world. The terrain is jagged, not with scattered peaks or isolated cliffs, but with vast fields of parallel ridges stretching across the horizon. New Horizons photographed these formations during its brief encounter, revealing rows of sharp blades arranged with striking regularity. The gaps between them range from roughly 3 to 5 kilometers, while the troughs separating neighboring ridges descend around 500 meters. At first glance, they seem impossible. Nothing similar had ever been observed on another planetary body. Scientists searching for comparisons found themselves looking not to distant worlds, but to Earth's highest mountains. The structures are known as penitentes. On Earth, penitentes form in the Andes, where intense sunlight slowly removes snow through sublimation. Sublimation is the process by which a solid transforms directly into gas without becoming liquid first. As sunlight removes material unevenly, narrow spires emerge, while shaded regions erode more slowly. The result is a forest of icy blades. Yet scale changes everything. Terrestrial penitentes are typically measured in centimeters or meters. A hiker may walk among them. On Pluto, the same process has operated for far longer and under very different conditions. The ridges rise hundreds of meters above their surroundings, exceeding the height of many skyscrapers and standing taller than the Empire State Building. Their composition is equally unusual. These formations are made primarily of methane ice. Over tens of millions of years, sunlight and atmospheric conditions have gradually sculpted the methane into the towering shapes observed today. No sudden event created them. They are products of extraordinary patience. Researchers worked to test this explanation. John Moores of York University and his colleagues developed simulations examining how sublimation could shape Pluto's surface. The models successfully reproduced both the spacing and the distinctive orientations seen in the real terrain. Several dominant alignment directions emerged naturally, matching observations from New Horizons. The match was compelling. Evidence suggested the blades were indeed carved through long-term sublimation rather than tectonic activity or impacts. Growth remains extremely slow. Current estimates indicate the ridges deepen by roughly 1 centimeter during each Pluto orbit around the Sunday. One orbit requires 248 Earth years. Entire human civilizations could rise and vanish while these formations change by only a few centimeters. Atmospheric conditions matter as well. Penitentes appear to develop most effectively during periods when atmospheric pressure increases. This requirement helps explain why similar landscapes have not been discovered on airless, icy worlds throughout the solar system. Without an atmosphere, the necessary balance between sunlight, sublimation, and surface conditions does not exist. Pluto occupies a rare middle ground. Its volatile ices, thin atmosphere, weak winds, and immense geological timescales combine to create an environment uniquely suited to producing the largest known penitentes anywhere. The result is a landscape of methane blades carved over millions of years by sunlight and atmosphere working together. Yet these towering ridges are only one expression of Pluto's complexity. Along the margins of its frozen heart, another landscape rises, built not from delicate erosion, but from mountains of astonishing strength. If you traced the edge of Sputnik Planitia from above, you would eventually arrive at a remarkable boundary where smooth plains suddenly give way to towering walls. The transition is abrupt. One moment, the landscape stretches flat across the basin floor. The next, mountains rise from the horizon. These are among Pluto's most impressive landforms. The ranges known as Al-Idrisi Montes, Norgay Montes, and Hillary Montes stand between roughly 2 and 3.5 kilometers above the surrounding terrain. Their steep slopes and rugged profiles would appear familiar on Earth, yet their composition makes them something entirely different. They are made of water ice. At Pluto's surface temperature of approximately negative 230 degrees Celsius, water ice no longer behaves like the brittle material you place in a drink. Under those conditions, it becomes extremely hard and structurally strong. In practical terms, it behaves more like granite than ordinary ice, capable of supporting enormous cliffs and mountains without collapsing. Their origin reaches deep into Pluto's past. Scientists believe many of these mountainous blocks are fragments of ancient crust disrupted during the colossal impact that formed the Sputnik Planitia Basin. Over billions of years, activity within the basin gradually rearranged these pieces, pushing and concentrating them along the margins. Yet the most fascinating part of the story involves motion. Several mountain blocks, some measuring tens of kilometers across, appear to rest within softer nitrogen ice rather than directly on solid ground. In images from New Horizons, they resemble giant icebergs scattered across a frozen sea. The comparison is surprisingly accurate. Water ice is less dense than nitrogen ice under Pluto's conditions. As a result, these enormous blocks can effectively float within the softer material surrounding them. The convective circulation operating beneath the basin slowly transports them from place to place. Over immense spans of time, they drift. Many gather along the boundaries between convection cells, where moving nitrogen ice concentrates them into chains and clusters. Some appear isolated. Others form irregular groups, extending across significant distances. Nothing comparable has been observed elsewhere. We know of no other location in the solar system where mountains composed of water ice are transported by flowing nitrogen ice. Pluto continues to reveal processes that seem almost invented. The contrast is extraordinary. Nitrogen ice creeps across the landscape at rates measured in centimeters per year. Riding atop it are blocks of rigid water ice large enough to rival mountain ranges. One material flows, the other resists. Together they create a landscape unlike any other known world. Movement extends beyond the basin itself. Nitrogen glaciers emerge through openings in the surrounding mountains and advance into lower terrain farther east. These glaciers form bright tongues stretching away from Sputnik Planitia, carrying volatile ice into neighboring regions. Their influence is easy to spot. Ancient impact craters east of the basin contain pools of accumulated nitrogen ice on their floors. Over time, glacial transport has partially filled them, creating the appearance of frozen lakes resting within older scars. This places Pluto in a remarkably exclusive group. Only three worlds are known to possess active glaciation today. Earth moves water ice. Mars transports carbon dioxide ice. Pluto moves nitrogen ice. Mountains floating atop frozen nitrogen, glaciers flowing through mountain passes, and impact craters slowly filling with icy deposits all exist on a world smaller than our moon. Yet, Pluto itself is only part of the story. Orbiting beside it is a companion unlike any other moon in the solar system, bound to Pluto in a relationship that challenges the very idea of what a planet and moon should be. Imagine placing two worlds in orbit around one another, then moving their balance point out into empty space between them. That sounds less like a planet and moon, and more like a paired system moving together through the darkness. Pluto and Charon belong to that rare category. Charon is enormous compared with its companion. Its diameter measures roughly 1,212 kilometers, more than half Pluto's diameter of approximately 2,377 kilometers. The mass ratio between them is only about 8.5 to 1, dramatically closer than any other known planet and moon pairing in the solar system. Because of that unusual relationship, the barycenter, meaning the shared center of gravity around which both bodies orbit, does not lie inside Pluto at all. It hangs in the space between them. As Pluto circles Charon, Charon circles Pluto as well. Each influences the other. Over immense spans of time, gravitational forces synchronize their motions. The result is mutual tidal locking. The same hemisphere of Pluto always faces Charon, and the same hemisphere of Charon always faces Pluto. Their rotations and orbital motion remain perfectly matched at approximately 6.387 Earth days. For an observer standing on Pluto, the effect would be extraordinary. From the hemisphere facing Charon, the moon would remain fixed in one position forever. It would never rise. It would never set. Instead, it would dominate the sky, appearing roughly 7 times wider than Earth's moon appears from our planet. Move to the opposite hemisphere, and the view changes completely. There, Charon never appears at all. Half of Pluto lives with a permanent companion overhead. Half never sees it once. This strange arrangement began near the birth of the solar system. Around 4.5 billion years ago, a large Kuiper Belt object collided with the young Pluto. Evidence suggests the impactor possessed between 1/3 and 1/2 of Pluto's mass. The collision was violent, yet unusually efficient. Unlike the event that formed Earth's moon, where debris gradually accumulated into a new body, Charon may have survived largely intact. Researchers sometimes describe this outcome as intact capture. That possibility helps explain why Pluto and Charon possess remarkably similar densities. The aftermath looked very different from the orderly system we know today. Charon likely orbited much closer to Pluto, following a stretched, eccentric path. Gravitational interactions gradually transferred energy between the two bodies. Over millions of years, Charon drifted outward while its orbit became more circular. Eventually, it settled at a distance of roughly 19,570 kilometers. But recent research has added another layer to the story. A study published in 2025 suggested that tidal friction generated during this long separation may have produced substantial internal heating within Pluto. As the pair adjusted to their modern configuration, energy was released deep inside the dwarf planet. That possibility carries profound implications. The collision that created Charon may also have helped create the ocean hidden beneath Pluto's frozen crust. In that sense, the two worlds remain connected not only by gravity, but by origin, history, and perhaps the very process that allowed liquid water to survive for billions of years. Viewed from a distance, Charon can appear like a simple companion world. Yet, when New Horizons returned detailed images, a far more complicated landscape emerged. The moon seemed divided into separate chapters written across its surface. The northern hemisphere tells one story. It is heavily cratered and ancient, preserving a record of impacts accumulated over immense spans of time. Much of this terrain has remained largely unchanged for billions of years. Craters overlap craters. Old scars remain visible. The surface carries the appearance of great age. Farther south, the character shifts dramatically. Broad, smoother plains spread across a region informally known as Vulcan Planum. Here the landscape looks younger and less battered. Long fractures cut through the terrain, creating a sense that powerful forces once reshaped the crust from within. One feature dominates them all. Serenity Chasma stretches across Charon's equatorial regions for at least 1,800 kilometers. In places, it reaches depths approaching 7.5 kilometers, deeper than the Grand Canyon on Earth. From orbit, it resembles a wound carved across an entire world. Its origin appears tied to water. Planetary scientists believe Charon once possessed a subsurface ocean of its own. As internal heat gradually faded, that ocean began to freeze. Water expands when it freezes, and the growing volume placed increasing stress on the surrounding shell. Eventually, the crust fractured. The immense canyon system preserved the evidence. The process unfolded long ago. Charon's smaller size allowed it to lose heat more rapidly than Pluto. While Pluto retained liquid water deep below its surface, Charon seems to have followed a different path. Its ocean froze completely, leaving only tectonic scars behind. But another feature immediately captures attention. Near the North Pole lies a dark reddish region known as Mordor Macula. Against Charon's gray terrain, the contrast is striking. The coloration appears almost painted onto the landscape. In a sense, it is. The reddish material consists of tholins, complex organic compounds produced through chemical reactions driven by sunlight. We have already encountered these compounds elsewhere in the Pluto system. Yet Charon presents a puzzle. It does not manufacture them in significant quantities itself. Instead, methane escaping from Pluto's atmosphere drifts across the gap separating the two worlds. That distance measures roughly 19,570 kilometers. Some of the methane reaches Charon's frigid polar regions and freezes onto the surface. Then sunlight takes over. Ultraviolet radiation breaks apart the frozen methane molecules and triggers chemical reactions that gradually build larger organic compounds. Over long periods, the pole acquires its distinctive reddish coloration. Pluto is literally altering its companion. One world releases material, the other collects it. The system extends beyond these two bodies. Four smaller moons, Nix, Hydra, Kerberos, and Styx, orbit the Pluto Charon pair. They range from roughly 7 to 65 kilometers across and consist largely of bright water ice. Their motions are unusual. Rather than rotating smoothly, they tumble unpredictably under the competing gravitational influences of the central binary. Their nearly circular orbits suggest a common origin, likely debris ejected during the same ancient collision that created Charon itself. Two worlds emerged from that event. One preserved an ocean, one lost its own, one releases methane, one gathers it. For 4.5 billion years, they have remained locked together, facing one another across the darkness between them. For a moment, leave the spacecraft behind, leave the maps, measurements, and models behind as well. Instead, imagine that you are standing on Pluto itself, not in a dream, but in a landscape reconstructed from everything New Horizons revealed. The first thing you notice is the light. The sun remains visible, yet it no longer resembles the broad disk we know from Earth. At Pluto's distance, it appears as an intensely bright point suspended in the darkness. Even so, it shines with roughly 250 times the brightness of a full moon seen from Earth. Your eyes would adapt, reading would still be possible. The shadows tell a different story. They stretch across the ground with softened edges, and local noon would feel more like deep terrestrial twilight than a typical day. Illumination exists, but only just. Lift your gaze higher. Near the horizon, a delicate blue haze traces the curve of the world. Layer upon layer of organic particles hang within the atmosphere, creating subtle bands that gradually fade upward into black space. The color comes from tholins, the same complex compounds that stain portions of Pluto's surface. The sky is present, yet it feels fragile. Temperature dominates everything else. The air hovers near negative 230 degrees Celsius. Exposed skin would freeze almost immediately. Beneath you, nitrogen ice forms a surface harder than concrete under terrestrial conditions. Then you become aware of something unusual. There is no familiar background of moving air. Pluto's atmosphere is extraordinarily thin, far too thin to carry sound in the way we experience on Earth. Wind would not reach your ears. Footsteps would not echo through the landscape. The world offers almost no acoustic company. Gravity changes your sense of movement as well. Pluto exerts only about 6% of Earth's gravitational pull. A person weighing 80 kilograms on Earth would effectively weigh about 5 kilograms here. Push gently from the ground, and you would rise several meters into the air before descending in a slow arc. Movement becomes graceful. Beneath your boots stretches Sputnik Planitia, a plain of bright nitrogen ice extending toward the horizon. The surface appears stable, yet it is slowly circulating through convection. Warmed from below, cooled from above, the ice drifts and overturns over immense timescales. The ground beneath you did not exist 500,000 years ago. 500,000 years from now, it will have changed again. Far away, mountains interrupt the plain. Walls of water ice rise roughly 3 kilometers above the surrounding terrain. At Pluto's temperatures, water ice behaves more like stone, creating sharp ridges and rugged peaks against the darkened sky. Look upward from the hemisphere facing Charon. The great moon hangs motionless overhead, fixed in place forever. Its gray surface is unmistakable. Near one pole, the reddish stain of mortar macula can be faintly distinguished. Charon occupies a region of sky roughly 7 times wider than Earth's moon, and below all of this lies another world. Approximately 50 kilometers of ice separate the surface from a hidden ocean. Between them rests a thin, insulating layer of methane clathrates. Beyond that waits dense, salty water that has remained liquid since before the earliest life emerged on Earth. You stand on a world once dismissed as frozen and inactive. Beneath your feet rests an ocean older than every complex organism that has ever lived on our planet. Long before planets settled into their modern arrangement, before continents existed on Earth, and before any ocean hid beneath Pluto's crust, the outer solar system was crowded with debris left over from creation itself. Pluto still lives among those remnants. Its home is the Kuiper Belt, a vast region extending beyond Neptune from roughly 30 to 50 times Earth's distance from the Sunday. Rather than a single ring, the Kuiper Belt is a sprawling population of icy bodies spread across immense distances. It occupies a frontier where sunlight weakens and temperatures remain perpetually low. Here, the past survives. The Kuiper Belt contains material that never became part of a major planet during the formation of the solar system, approximately 4,600,000,000 years ago. Fragments of rock and ice remained behind, while larger worlds gathered mass closer to the Sunday. Pluto is the largest known member of this population, yet it is far from unique. Astronomers have cataloged thousands of Kuiper Belt objects, and estimates suggest millions more remain undiscovered. Most are much smaller than Pluto. Some may rival it in size. Countless others drift through darkness beyond the reach of current surveys. Many share the same ingredients: nitrogen ice, methane ice, carbon monoxide ice, and water ice were abundant in the frigid outer regions of the young protoplanetary disk, meaning the rotating cloud of gas and dust from which the solar system emerged. Pluto formed within that environment and retains much of that ancient chemistry today. Its orbit reflects that early history as well. At first glance, Pluto appears to cross Neptune's path, yet the two worlds never collide. A gravitational arrangement known as orbital resonance keeps them safely separated. Orbital resonance occurs when two bodies complete their journeys around the Sun in a repeating mathematical pattern. For Pluto and Neptune, the ratio is 3 to 2. Every time Neptune completes 3 orbits, Pluto completes exactly 2. The timing remains remarkably precise. Their motions stay coordinated across billions of years. This relationship likely emerged during a dramatic period of planetary migration. Evidence suggests Neptune slowly moved outward after its formation. As it traveled, its gravity disturbed surrounding debris and reshaped the architecture of the outer solar system. Many Kuiper Belt objects were scattered into new orbits. Pluto became locked into resonance during that process and has remained there ever since. The surface itself may preserve material from that distant era. Some researchers believe portions of Pluto's nitrogen ice are primordial, meaning they originated during Pluto's formation rather than through later geological recycling. If correct, the frozen plains contain substances that have existed since the birth of the solar system. In that sense, Pluto is more than an active world. It is also a record. While mountains rise, glaciers flow, and hidden oceans persist below, part of Pluto still carries the chemical signature of the environment from which every planet emerged. We are looking at a body that bridges beginning and present, preserving clues from both. That perspective changes the significance of everything we have seen so far. If a world this small, this distant, and this ancient can preserve liquid water for the entire history of the solar system, then Pluto may represent something larger than itself. It may be evidence that enduring oceans are not rare exceptions, but natural outcomes waiting throughout the outer darkness, far beyond the familiar planets, where sunlight arrives weakened by distance and temperatures remain near the edge of physical possibility, a scientific assumption quietly unraveled. For decades, ocean worlds seemed to follow a pattern. Every confirmed example circled a giant planet. Europa traveled around Jupiter. Enceladus and Titan belonged to Saturn. Ganymede moved through Jupiter's immense gravitational domain. In each case, the explanation appeared straightforward. The giant planet continuously stretched and compressed its moon through tidal forces, meaning gravitational squeezing caused by changing orbital positions. That flexing generated heat deep inside the moon and prevented subsurface water from freezing solid. The mechanism seemed universal. If you wanted an ocean beneath ice, you needed a giant planet nearby. Pluto changed that expectation. Unlike those moons, Pluto drifts through space alone. Its average distance from the Sun is approximately 39 astronomical units, with an astronomical unit being the distance between Earth and the Sunday. No Jupiter looms overhead. No Saturn tugs at its interior. No massive neighbor needs its crust and supplies extra warmth. Yet an ocean remains. That single fact carries enormous consequences. Everything we have explored points toward a body sustained by different rules. Radioactive elements buried within Pluto's rocky interior release heat through gradual decay. Additional warmth may have been trapped during formation or generated during the ancient collision that created Charon. Above the ocean sits an insulating layer that slows heat loss and preserves liquid conditions across immense stretches of time. The recipe is surprisingly simple. Heat below, insulation above. For years, many researchers viewed tidal heating as the essential ingredient, but Pluto demonstrated that another pathway exists. A world does not necessarily require a giant planetary companion to maintain internal water. Under the right conditions, it may achieve the same outcome independently. That realization expanded the map. The Kuiper Belt contains a staggering number of objects. Astronomers estimate hundreds of thousands exceed 100 kilometers in diameter. Many likely share similar ingredients, including water ice, methane, nitrogen, carbon monoxide, and rocky interiors capable of generating modest amounts of heat. Most remain unexplored. Some could possess hidden oceans as well. Attention quickly turned toward other dwarf planets. Eris, slightly smaller than Pluto yet more massive, became an obvious candidate. Makemake entered the discussion. So did Haumea. Each preserves clues from the distant solar system, and each may conceal far more complexity than surface observations alone suggest. Researchers at Hokkaido University reached a striking conclusion. Gas hydrate insulation, the same process proposed for Pluto, may represent a broadly applicable mechanism capable of maintaining long-lived oceans inside minimally heated icy bodies. The implication extends far beyond a single dwarf planet. What happens if Pluto is ordinary rather than exceptional? A handful of ocean worlds suddenly becomes dozens. Dozens may become hundreds. Across our galaxy, the number could rise into the billions. Hidden seas may exist beneath ice shells scattered through planetary systems everywhere, protected by physics that remained overlooked for generations. And whenever liquid water persists for billions of years, chemistry follows, energy follows, complexity follows. Eventually, every discussion arrives at the same destination, regardless of how distant the world may be: the possibility of life. A single question now sits beneath everything we have learned. Not a question of geology, not a question of classification, something deeper. Could a hidden ocean beneath Pluto's ice support life? Today, that is no longer a speculative idea reserved for fiction. It is an active scientific topic discussed in peer reviewed research because Pluto appears to satisfy several conditions that astrobiologists consider essential when evaluating potentially habitable environments. The word habitability carries a specific meaning. It does not imply forests, animals, or breathable air. In astrobiology, habitability simply refers to whether an environment can support chemistry associated with living systems. Scientists generally focus on three requirements: liquid water, a source of energy, and access to useful chemical ingredients. Pluto may possess all three. The first requirement appears strongest. Multiple independent observations point toward a persistent subsurface ocean. Geological deformation, gravity measurements, crustal behavior, and models of Sputnik Planitia all converge on the same conclusion. Liquid water exists. The second requirement concerns energy. Even at Pluto's immense distance from the Sun, energy can originate from within. Radioactive elements inside the rocky core release heat through gradual decay. That process has likely operated for billions of years. Some researchers also consider the possibility of hydrothermal activity, meaning hot water circulating through rock near the ocean floor. If such environments exist, chemical reactions could continuously provide usable energy. Life does not require sunlight. Earth demonstrates that clearly. Far beneath the ocean's surface, hydrothermal vent ecosystems thrive in complete darkness. Bacteria extract energy directly from chemistry emerging from the planet's interior. Entire food webs depend on those reactions rather than solar radiation. Another requirement is chemistry. Here, Pluto again appears promising. Evidence suggests the ocean may contain dissolved salts and ammonia. Ammonia functions as a natural antifreeze, helping water remain liquid under extremely cold conditions. Organic compounds may also be present, either inherited from Pluto's formation or released gradually from the rocky interior. We have seen comparable environments on Earth. Lake Vostok in Antarctica remains buried beneath roughly 4 kilometers of ice. It has been isolated for immense periods of time, yet microbial life has been detected in association with that hidden environment. Similar communities survive beneath glaciers in Greenland and Iceland, enduring cold temperatures, darkness, and unusual chemistry. The parallels are striking. Time may be another important factor. If the hot start model is correct, Pluto's ocean formed near the beginning of the solar system approximately 4.5 billion years ago. That means any chemistry within the ocean has potentially had as much time to develop as chemistry on Earth. During that same span, our planet produced everything from microscopic organisms to vast ecosystems. But scientific honesty matters here. No probe has sampled Pluto's ocean, no instrument has detected biology, no observation provides direct evidence that life exists there. Extreme salinity, very low temperatures, and ammonia-rich conditions could prove difficult for living systems as we understand them. The answer remains unknown. Yet whether life exists beneath Pluto's ice or not, the discovery has already transformed the search itself. A world once dismissed as frozen and inactive expanded the boundaries of possibility, showing that places capable of supporting life may exist far beyond the regions where anyone first thought to look. For much of modern astronomy, a simple picture guided our search for life. Imagine drawing a ring around a star. Too close, and water boils away. Too far, and it freezes solid. Somewhere between those extremes lies a region where liquid water can exist on a planet's surface. Scientists called this the habitable zone, often nicknamed the Goldilocks zone because conditions are neither too hot nor too cold. The idea was useful. It helped researchers identify promising worlds and compare planetary environments. Earth sat comfortably within this region. Mars lingered near its outer boundary. Beyond the orbit of Jupiter, the solar system seemed to fade into a realm of deep cold where liquid water appeared increasingly unlikely. That framework shaped expectations for decades. Yet, as spacecraft ventured farther outward, a different story emerged. Europa revealed evidence for a hidden ocean beneath ice. Enceladus launched water-rich plumes into space. Titan showed signs of a buried sea beneath its frozen crust. Then Pluto joined the list, carrying an ocean beneath a shell of ice at the edge of the known planetary system. Each discovery widened the picture. None of these worlds depend on sunlight to maintain their liquid water. Their surfaces remain frozen. Their oceans survive below. The source of warmth comes from within rather than above. That distinction changes everything. Internal heat can arise through several pathways. Radioactive elements slowly release energy over billions of years. Gravitational interactions can flex a world's interior and generate frictional heating. Ancient formation processes may leave reservoirs of primordial warmth, meaning heat retained from the body's birth. Combined with insulating layers that slow energy loss, these mechanisms can preserve liquid water long after traditional models predict freezing. Suddenly, habitability becomes less dependent on distance from a star. A frozen exterior no longer guarantees a frozen interior. As you follow that idea outward, the implications become difficult to ignore. An icy object does not need blue skies, mild temperatures, or surface oceans to possess environments where chemistry remains active. It may simply need sufficient mass, internal energy, and materials capable of trapping heat. The solar system alone contains countless candidates. Beyond Neptune, the Kuiper Belt stretches across vast distances and contains an enormous population of icy worlds. Many remain only faint points of light in telescopes. Some may hide oceans, much like Pluto's, waiting for future missions to reveal them. But the idea reaches even farther. Astronomers have identified evidence that some planets are ejected from their native systems entirely. These rogue planets wander interstellar space without orbiting any star. Under traditional definitions, such worlds seemed hopelessly uninhabitable. Yet, internal heat, combined with insulating layers, could, in theory, preserve subsurface oceans even in the darkness between stars. The numbers begin to change rapidly. Worlds once excluded from consideration return to the map. Environments once dismissed become scientifically plausible. The potential inventory of habitable places may increase not by a small margin, but by orders of magnitude across the Milky Way. And that is Pluto's most far-reaching contribution. It did not merely transform our understanding of one distant dwarf planet. It expanded the boundaries of where possibility itself can exist. There is a remarkable imbalance at the heart of Pluto's science. The farther we traveled from Earth, the less time we had. After nearly 9.5 years crossing the solar system, New Horizons entered the Pluto system at approximately 50,000 kilometers per hour. At that speed, there would be no lingering arrival, no extended survey, no opportunity to circle back for another look. Everything depended on momentum. The spacecraft carried no fuel capable of slowing it into orbit. No landing system waited aboard. No mechanism existed for descending onto the surface. Engineers designed a flyby mission because any alternative would have required far greater mass, cost, and propulsion capability than available technology could reasonably provide at the time. So New Horizons raced through. Roughly 30 hours, that was the encounter. From that brief passage came nearly everything we have discussed: evidence for an ocean, measurements of atmosphere and haze, maps of glaciers, mountains, cryovolcanoes, and tectonic fractures, clues about Pluto's interior, hints of processes still shaping the surface today. An extraordinary harvest of information, yet it all emerged from a single visit. Once the encounter ended, New Horizons continued outward into deeper regions of the Kuiper Belt. The mission was not finished. A new destination awaited. On January 1st, 2019, the spacecraft passed Arrokoth, a small Kuiper Belt object approximately 36 kilometers long. At a distance of roughly 6.5 billion kilometers from the Sun, it became the most distant object ever explored up close. Arrokoth looked unlike any world previously visited. Two flattened lobes rested together in contact, forming what scientists call a contact binary, meaning two separate bodies that merged gently rather than through a destructive collision. The structure preserved evidence from the solar system's earliest era, suggesting planetary building blocks sometimes assembled through remarkably slow encounters. Even farther outward, New Horizons continued its journey. By late 2024, it had traveled beyond 60 times the Earth-Sun distance. That placed it roughly twice as far from the Sun as Pluto had been during the historic flyby. Despite the distance, the spacecraft remained operational, conserving power from its plutonium energy source while studying dust, particles, radiation, and the broader Kuiper Belt environment. The mission goes on, but Pluto remains behind. Several teams have proposed future missions. Orbiter concepts have been studied. Detailed investigations have examined propulsion methods capable of slowing a spacecraft after a decade or more of travel. Each proposal confronts immense engineering challenges, along with competition from every other major objective in planetary science. More ambitious ideas exist as well. Researchers have imagined probes capable of penetrating thick ice shells to reach hidden oceans. Similar concepts have been explored for Europa, but adapting such technology for Pluto would require operating at distances nearly 7 times farther from the Sun, under conditions that remain extraordinarily demanding. Meanwhile, the Kuiper Belt stretches outward, almost untouched. New Horizons has visited exactly 2 objects among potentially billions. We discovered an ocean that may have endured for 4.5 billion years, yet no approved mission exists to return. As you consider that vast span of time and distance, the realization feels both humbling and strangely profound. Maps often create an illusion of completeness. When we see a world covered in names, colors, and labeled features, it becomes easy to assume the exploration is finished. Pluto can give that impression. We have traced glaciers across its plains, measured mountains along its horizons, examined atmospheric layers above its surface, and inferred the existence of an ocean hidden far below. Yet, a surprising gap remains. A substantial portion of Pluto still exists, beyond the reach of detailed observation. The reason lies in timing. Pluto rotates slowly. One complete rotation requires approximately 6.387 Earth days. New Horizons, meanwhile, cross the Pluto system in roughly 30 hours. The spacecraft arrived, gathered its data, and departed long before the dwarf planet could fully turn beneath it. As a result, the hemisphere facing the spacecraft during closest approach became the focus of nearly every iconic image. That side received extraordinary attention. Some regions were photographed at resolutions capable of revealing features only a few hundred meters across. The level of detail was astonishing. Elsewhere, the view was different. During the long approach phase, New Horizons observed Pluto from much greater distances. Those observations allowed scientists to see all longitudes over time as the planet slowly rotated. Broad patterns emerged. Large, bright, and dark regions became visible. Major terrain provinces could be identified, but the fine details remained out of reach. Resolution decreases rapidly with distance. Imagine viewing a mountain range from an airplane rather than standing beside it. You can recognize the landscape, yet smaller structures disappear. Individual cliffs, valleys, and ridges blend together into larger shapes. That is essentially the situation on Pluto's far hemisphere. We know it exists. We know some of its broad geography, but we do not truly know it. Could additional cryovolcanic regions lie there, comparable to Wright Mons and Picard Mons? The available images cannot answer that question. Might enormous mountain chains stretch across unseen terrain? Could different mixtures of nitrogen, methane, and water ice dominate regions beyond the hemisphere we explored in detail? Those possibilities remain open. The mystery extends below the surface as well. If Pluto's ocean interacts with the crust, signs of that interaction may appear in places we have never examined closely. Variations in ice shell thickness, tectonic fractures, uplifted terrain, or regions of enhanced heat flow could provide valuable clues about the interior structure. Some of the strongest evidence may reside on landscapes still unresolved. That uncertainty is remarkable when you consider what the encounter hemisphere already revealed. Within the half we studied closely, scientists found convecting nitrogen plains, active glacial flow, towering water ice mountains, cryovolcanic structures, atmospheric haze, exotic weather cycles, and evidence for a long-lived ocean beneath the crust. All of that emerged from one side. The other side remains largely unknown. In many ways, that makes Pluto unlike the thoroughly mapped worlds closer to Earth. It still retains a frontier. We have crossed millions of kilometers to glimpse it, uncovered discoveries few expected, and transformed our understanding of distant planetary bodies. Yet half the world continues to wait beyond the edge of detailed exploration, holding answers to questions we have not learned to ask. A measurement can change more than a map. Sometimes it changes the assumptions beneath the map as well. For much of modern planetary science, size carried an expectation. Large worlds were thought to possess the resources needed for long geological lives. They retained heat longer. They sustained internal activity. They developed complex histories written into their landscapes. Smaller bodies occupied a different category. They were expected to cool rapidly. They were expected to become static. They were expected to fade into geological retirement long before the present day. That framework seemed reasonable. After all, Pluto's diameter measures only about 2,377 kilometers. It is smaller than Earth's moon. It resides nearly 40 times farther from the Sun than Earth. No giant planet stretches and compresses its interior through tidal forces. No thick atmosphere wraps it in substantial warmth. By every traditional expectation, Pluto should have been simple. Instead, it became a lesson. As the evidence accumulated from New Horizons, one assumption after another gave way. Beneath an icy crust lay signs of a long-lived ocean. Across Sputnik Planitia, nitrogen ice circulated through convection, a process in which warmer material rises while cooler material sinks. Glaciers flowed, surface materials migrated, atmospheric cycles reshaped the landscape over immense spans of time. Even cryovolcanoes appeared. A cryovolcano is a volcano that erupts liquids such as water and ammonia, instead of molten rock. Pluto seemed to possess some of the largest examples known. The pattern became difficult to ignore. Complexity had emerged where simplicity was expected. You can compare Pluto with larger worlds, and the contrast becomes striking. Mercury exceeds Pluto in size and mass, yet much of its visible surface preserves records from ancient eras. Numerous moons throughout the solar system appear comparatively unchanged. Pluto, meanwhile, displays evidence of renewal, transport, circulation, and interaction between atmosphere, surface, and interior. Its scale did not predict its behavior. That realization carried consequences beyond a single dwarf planet. Researchers began reconsidering how geological activity survives. Internal heat, insulation, chemistry, and history could matter as much as sheer size. A small world might remain dynamic if the right conditions persist over billions of years. Pluto became a demonstration. Then there is the timing. In 2006, the same year the spacecraft departed Earth, the International Astronomical Union reclassified Pluto as a dwarf planet. The decision rested on orbital dynamics, particularly the requirement that a planet must clear its orbital neighborhood of comparable objects. The debate that followed never fully disappeared. Yet, New Horizons altered the conversation. The mission did not address definitions. It revealed realities. Scientists found a world with layered atmospheric processes, active surface modification, internal structure, and extraordinary diversity. Whatever category Pluto occupied, it was far richer than many had imagined. That may be the deepest lesson of all. Nature does not organize itself according to our expectations. Worlds are not required to become dull because they are small. They do not surrender complexity because they orbit in distant darkness. We looked toward a body many considered too small, too cold, and too remote to matter greatly. It answered with glaciers, weather, mountains, volcanoes, and beneath it all, an ocean. Long before the glaciers, before the atmosphere, before the ocean hidden beneath kilometers of ice, there was a moment when two growing worlds crossed paths in the outer solar system. We can trace much of Pluto's present character back to that ancient encounter, a collision that occurred roughly 4.5 billion years ago while the planets were still settling into their modern arrangement. The impactor was enormous. Models suggest a Kuiper Belt object between 1/3 and 1/2 of Pluto's mass approached on an oblique trajectory. Rather than striking head-on, it clipped Proto-Pluto at an angle. The event released staggering amounts of energy, yet the geometry mattered. Both bodies survived. That outcome changed everything. Many giant impacts end in destruction or complete merger. This one appears to have produced something rarer. A substantial portion of material was displaced, redistributed, and reshaped, while the two principal bodies remained largely intact. From that process emerged Charon, already familiar to us as Pluto's constant companion. The collision did more than create a moon. Immense heat flooded Pluto's interior. Rock, ice, and volatile compounds were compressed, fractured, and stirred together. According to recent studies, this early heating episode may have generated the initial liquid water reservoir beneath the crust. Later, insulating layers preserved that warmth, but the beginning may have occurred here, during a brief interval when kinetic energy became internal heat. The aftermath continued unfolding. Material thrown outward did not simply disappear into space. Debris remained gravitationally bound to the new Pluto-Charon system. Over time, it gathered into smaller bodies, eventually forming Nix, Hydra, Kerberos, and Styx. Each moon became a surviving fragment of that primordial catastrophe, circling the binary pair billions of years after the event itself. The basin we know as Sputnik Planitia may also carry the imprint of this ancient encounter. Whether the collision directly excavated the structure or deepened an earlier depression remains debated, yet the connection appears profound. The vast hollow later collected nitrogen ice and evolved into the geological center of Pluto's modern activity. But the consequences extended even further. As Charon gradually migrated outward, tidal forces reshaped the system. Tidal forces are gravitational pulls that stretch and deform bodies over time. The orbit expanded, rotations slowed. Eventually, both worlds became mutually locked, each always showing the same face to the other. That evolving relationship influenced stress patterns within Pluto's crust and helped determine the long-term distribution of mass across the system. Seen from this perspective, many seemingly separate discoveries begin to converge. The ocean, the binary partnership, the five-moon system, the heart-shaped basin, and the enduring geological activity all lead back toward a single origin. One impact, one extraordinary chain of consequences. A brief episode near the birth of the solar system set countless processes in motion. Across 4.5 billion years, those processes never entirely stopped. Beneath Pluto's frozen surface, the ocean born from that ancient upheaval has endured, carrying the legacy of that collision into the present day. A spacecraft crossing a plume changed the direction of an entire field. When the Cassini mission arrived at Saturn, Enceladus was not expected to become one of the most important places in astrobiology. It is a small moon, only about 504 kilometers across, orbiting deep within Saturn's gravitational system. For many years, it occupied a relatively modest place in scientific discussions. Then came the flybys. In 2005, Cassini passed through towering plumes erupting from fractures near Enceladus's south pole. These fractures, later nicknamed tiger stripes, were releasing material directly into space. What initially appeared unusual soon became extraordinary. The plumes contained water vapor. Then came additional discoveries. Scientists identified salts within the ejected material. Organic compounds appeared as well. Perhaps most importantly, instruments detected molecular hydrogen, a form of hydrogen gas that on Earth is often associated with hydrothermal activity. Hydrothermal activity occurs when water interacts with heated rock, creating chemical reactions capable of supplying energy. Suddenly, a new picture emerged. Beneath Enceladus's frozen crust lay a global ocean. Deep below that ocean, the seafloor appeared chemically active. Material from the interior was escaping into space, where a passing spacecraft could sample it directly. The implications were profound. Until then, discussions of habitability often centered on planets with temperate surfaces. Yet here was a tiny, icy moon, far beyond the traditional region associated with liquid water, displaying conditions that satisfied several important requirements for life, as astrobiologists define it. The lesson arrived gently. Small worlds could remain active. Ocean environments could survive beneath ice. Distance from the sun was not necessarily decisive. Even so, Enceladus still possessed an advantage. Saturn's gravity constantly flexes the moon during its orbit. This process, known as tidal heating, generates internal warmth through friction. Scientists could point to a clear external energy source helping maintain the ocean. That explanation worked well. Then Pluto entered the conversation. As our understanding expanded, the contrast became impossible to ignore. Pluto resides far beyond Saturn. No giant planet stretches its interior. No powerful tidal engine continually supplies heat, yet evidence accumulated for a long-lived ocean beneath its surface, preserved across billions of years. The comparison changed the scale of the discussion. Enceladus demonstrated that ocean worlds existed. Pluto suggested they might exist under far broader circumstances. Internal radioactive heat, ancient formation energy, and insulating materials could potentially sustain liquid water without help from a nearby giant planet. But this shift affected more than planetary science. It reshaped astrobiology itself. Researchers increasingly began looking beyond the traditional habitable zone, the region around a star where surface water can remain liquid. Beneath ice shells, oceans may persist in places once dismissed as permanently frozen. These hidden environments could outnumber Earth-like surfaces by a substantial margin. You can feel the change in the questions scientists ask today. Attention is turning inward rather than outward, beneath crusts rather than across landscapes, toward chemistry occurring far from sunlight. What began with erupting plumes above a small moon eventually expanded into a larger realization. Worlds do not need blue skies, mild temperatures, or open oceans to remain interesting. The search for life is no longer focused solely on finding another Earth. Increasingly, it has become a search for another ocean. Time is difficult to picture when the numbers become too large. We can imagine a century. We can stretch toward 1,000 years. Even 1,000,000 begins to lose shape. But beneath Pluto's crust lies something that has endured for roughly 4.5 billion years, nearly the entire age of the solar system itself. To appreciate that span, we need a different perspective. When Pluto's ocean likely formed, Earth was a vastly different place. Our planet was still emerging from its violent beginnings. Vast regions remained molten. The moon had only recently taken shape following its own giant impact. Stable oceans had not yet settled across Earth's surface. The chronology is astonishing. Hundreds of millions of years passed before the earliest persistent bodies of water appeared here. During that interval, the hidden ocean beneath Pluto may already have existed beneath its growing shell of ice, sealed away from space, while the inner solar system continued cooling and changing. Then life arrived on Earth. Evidence suggests the earliest single-celled organisms emerged around 3.8 billion years ago. By then, Pluto's buried ocean had already endured for roughly 700 million years. It was ancient, long before biology left its first known traces on our world. The ages continue to accumulate. Around 2.4 billion years ago, photosynthetic organisms transformed Earth's atmosphere. Photosynthesis is the process by which organisms use light to convert carbon dioxide and water into energy-rich compounds. That transformation eventually filled the atmosphere with oxygen and altered the future of life. Yet, Pluto's ocean was already more than 2 billion years old. Much later, animals appeared. The earliest complex animal life emerged roughly 600 million years ago. Entire evolutionary histories followed, oceans filled with unfamiliar creatures, forests spread across continents, dinosaurs rose and disappeared, mammals diversified. Humanity arrived only moments ago by comparison. Still, the ocean remained. Every civilization unfolded during that same interval. Every empire, every migration, every language, every work of art, every scientific discovery, every generation that has ever lived occupied a brief chapter while liquid water persisted beneath Pluto's frozen surface. But what makes this story remarkable is not merely age, it is location. No sunlight reaches that water. No waves roll across its upper boundary. Above it rest kilometers of ice, dense layers of frozen material separating the ocean from the sky. The environment exists in perpetual darkness, isolated from the familiar rhythms that shape seas on Earth. And yet it survived. Modern research suggests methane clathrate insulation, proposed only in 2019, may have helped preserve that ocean across billions of years. Clathrates are crystalline structures in which water molecules form cage like frameworks around trapped gas molecules. Acting as an insulating barrier, they may have slowed heat loss enough for the ocean to endure. You can almost feel the scale of that realization. A vast body of liquid water has existed beyond Neptune for the lifetime of the solar system, hidden from view until very recently. There is something deeply compelling about that, not because it is dramatic, but because it endured. Unseen, unchanged in ways we can scarcely measure, it remained there while nearly everything else we know passed through countless transformations. Attached to the interior of New Horizons was an object weighing only 30 grams. Compared with the spacecraft, it was insignificant. Compared with the discoveries that followed, it was smaller still. Yet among everything carried toward Pluto, it held a uniquely human significance. Inside, a small aluminum canister rested a portion of Clyde Tombaugh's ashes. The inscription was personal rather than technical. It described a discoverer, a teacher, a husband, a father, a friend. Long before spacecraft crossed the outer solar system, Tombaugh had been a young man studying the night sky from rural Kansas, fascinated by objects too distant for most people to imagine. His beginnings were modest. He built one of his earliest serious telescopes using tractor parts and scrap materials available on the family farm. Formal credentials did not open the door for him. Curiosity did. Skill did. Patience did. Eventually, those qualities brought him to the search for a mysterious world beyond Neptune. The process was painstaking, using photographic plates and a device called a blink comparator, a machine that rapidly alternates between two images to reveal moving objects. Tombaugh examined the sky piece by piece. Night after night, he searched for a faint point of light, shifting against a fixed background of stars. In 1930, he found it. Pluto entered human awareness not through a dramatic revelation, but through careful observation and persistence. The object appeared as a tiny speck on photographic plates. No mountains were visible. No atmosphere. No glaciers. No ocean. Only a dot. For decades, that dot remained largely mysterious. Even as telescopes improved, Pluto revealed little of its true nature. Tombaugh lived through much of that period. He watched scientific understanding advance, yet the world he discovered remained frustratingly distant. Then time intervened. He died in 1997. New Horizons would not launch until 2006. Pluto's reclassification as a dwarf planet came afterward. The historic flyby occurred in 2015. The evidence for a subsurface ocean emerged through years of analysis that followed. He never saw any of it, but his journey continued. When New Horizons swept past Pluto on July 14, 2015, Tombaugh's ashes crossed the system alongside the spacecraft. They traveled with the instruments that revealed nitrogen glaciers, convecting ice, towering mountains, atmospheric hazes, and signs of an ocean hidden beneath the crust. There is something remarkable in that sequence. The man who first identified a distant moving point never learned what that world contained. The technology required to uncover those secrets did not exist during his lifetime. Even the theories explaining Pluto's buried ocean would not appear until decades after his death. Yet he remained part of the mission. Today, his ashes continue outward, beyond Pluto and beyond Arakoth, carried deeper into the Kuiper Belt at roughly 50,000 kilometers per hour. They are the farthest known human remains from Earth, moving through a region he helped bring into humanity's awareness. He discovered a world with a blink comparator and extraordinary patience. Generations later, we followed his path, and the world waiting there turned out to be far larger, stranger, and more alive than anyone in 1930 could possibly have imagined. In August of 2006, before New Horizons had even left the inner solar system, a vote took place at the General Assembly of the International Astronomical Union. The decision would become one of the most debated moments in modern astronomy. Pluto was reclassified. Under the new definition, a planet had to satisfy three conditions. It must orbit the Sunday. It must possess enough mass for gravity to shape it into a nearly spherical form, and it must have cleared its orbital neighborhood of comparable objects. Pluto fulfilled the first requirement. It fulfilled the second as well. The third proved more difficult. Beyond Neptune lies a vast population of icy bodies. Pluto shares that region. As a result, it was assigned a new category, dwarf planet. The vote itself was relatively narrow. Public reaction was anything but. Scientists, educators, and enthusiasts argued for years afterward, and many continue to do so today. Yet as we drift farther into Pluto's story, something curious emerges. The debate concerns classification. The discoveries concern reality. While definitions occupied headlines, the world itself remained largely unknown. At the time of the vote, nobody had seen nitrogen glaciers flowing across a frozen basin. Nobody knew of convecting ice plains, towering water ice, mountains, atmospheric hazes, cryovolcanic structures, or compelling evidence for a buried ocean. Those revelations came later, and they transformed the conversation. Looking back, the list of mistaken assumptions is surprisingly long. We believed Pluto was geologically inactive. We assumed a body this small should have lost most internal heat long ago. We expected a distant object in the Kuiper Belt to preserve ancient scars rather than continually reshape itself. The evidence disagreed. We also thought long-lived oceans in the outer solar system required substantial tidal heating from a giant planetary companion. Europa experiences that influence from Jupiter. Enceladus receives it from Saturn. Pluto circles the Sun without such assistance, yet signs point toward liquid water enduring beneath its crust for billions of years. That realization reached far beyond one world. It challenged a framework. Perhaps the most important correction involved habitability itself. Entire categories of objects once dismissed as frozen relics suddenly became candidates for hidden oceans. The map changed. The questions changed. Even the places worth exploring changed. But none of this represents a failure. It represents the process working. Science begins with incomplete information. We build explanations from the evidence available. Then new observations arrive. Sometimes they confirm expectations. Sometimes they overturn them. When the data change, the models follow. That is exactly what happened here. Nature offered an answer nobody anticipated. Again and again, the history of exploration reveals a similar pattern. Worlds described as barren later reveal complexity. Landscapes, expected to be simple, become astonishingly diverse. The farther we travel, the more often certainty gives way to surprise. Pluto stands among the strongest examples. A distant point of light became a dynamic world. Yet the deeper lesson reaches beyond Pluto itself. Across the Kuiper Belt, countless objects continue their slow journeys around the Sunday. Most remain unresolved dots, even in powerful telescopes. Their surfaces, interiors, and histories are still hidden from us. So far, we have opened exactly two books. The library remains almost entirely unread. Far beyond the orbit of Neptune, beyond the familiar architecture of planets and moons, our maps begin to fade. Names become sparse. Observations become fragmentary. The certainty we carry through the inner solar system gradually gives way to possibility. Yet possibility has become far more interesting than it once seemed. A decade ago, many of these distant worlds were regarded as frozen leftovers, small points of light, ancient debris, valuable for understanding planetary formation perhaps, but unlikely to possess active interiors or enduring reservoirs of liquid water. Pluto changed that expectation. Once the evidence for its buried ocean began to accumulate, an uncomfortable question emerged. If Pluto can do this, why not others? Consider Eris, slightly smaller in diameter than Pluto, but more massive overall. It travels at an average distance nearly 3 times farther from the Sunday temperatures. There are even lower. Sunlight is weaker still. Yet if Eris possesses a similar mixture of rock, water ice, volatile compounds, and insulating methane clathrates, then a hidden ocean becomes difficult to dismiss outright. The possibility extends further. Makemake, Haumea, Gwawar, Gongong, Sedna. Each follows a different path through the outer darkness. Each preserves clues from the solar system's earliest history. Most remain little more than distant observations collected through powerful telescopes. We know their sizes, we estimate their compositions, but their interiors remain concealed. The same was true of Pluto. For decades, beyond these named worlds lies an even larger frontier. The scattered disk contains objects flung onto elongated orbits by ancient gravitational encounters. Farther still, the hypothetical Oort cloud may surround the solar system like a vast shell, extending perhaps halfway toward the nearest star. The numbers become staggering, not thousands, potentially trillions. Most of those bodies will be small, many will be inert. Yet, if methane clathrate insulation represents a common physical process rather than a rare exception, then liquid water may persist beneath the surfaces of far more worlds than we once imagined. That realization reshapes more than planetary science. It reshapes perspective. For generations, discussions of habitability focused on planetary surfaces warmed by nearby stars. The search centered on Earth-like conditions because Earth provided the only known example. But nature may have chosen a broader strategy. Instead of scattering life-friendly environments across exposed landscapes, perhaps it concealed many of them beneath protective shells of ice. What if liquid water most often survives out of sight? What if chemistry unfolds beneath frozen crusts rather than beneath open skies? As astronomers discover thousands of planets around other stars, one pattern continues to emerge. Rocky worlds occupying traditional habitable zones appear valuable, but icy bodies and frozen moons appear vastly more common. Orders of magnitude more common. If even a fraction contain hidden oceans, then the universe may be crowded with environments capable of supporting complex chemistry. Most would never see sunlight. Most would never possess blue skies or green continents. Their waters would remain buried beneath kilometers of ice, isolated from the cosmos above. And perhaps that is the deepest lesson Pluto offered us. The universe may be full of dark oceans, Pluto was the first one we found. It will not be the last. Long before the first forests spread across Earth, before continents settled into their familiar forms, before the earliest animals moved through ancient seas, an ocean already existed beneath Pluto's frozen crust. It remains there today. We have followed evidence toward it through geology, physics, orbital evolution, and the subtle shape of a distant world's surface. Piece by piece, the picture emerged, beneath layers of nitrogen ice, beneath mountains of water ice harder than stone, beneath insulating methane clathrates, liquid water endures, and it has endured for almost the entire history of the solar system. Consider what that means. When Earth was still gathering itself from impacts and molten rock, that ocean may already have been present. As the first stable oceans formed here, another ocean rested far beyond Neptune. When the earliest microbial life appeared on our planet, Pluto's hidden waters were already ancient. A vast span of time. Yet time is only part of the story. No visible sunlight has ever reached those depths. Not once. The ice shell above stretches for tens of kilometers. Every photon arriving from the distant sun is stopped long before reaching the water below. Across roughly 4.5 billion years, that darkness has remained unbroken. The ocean does not know day. It does not know seasons. It does not know sunrise. Far overhead, Pluto circles the sun every 248 Earth years. Atmospheres freeze and return. Glaciers flow. Surface ice migrates from one region to another. But beneath that changing exterior, the ocean remains separated from the sky by barriers no human technology has crossed. We have never touched it. No spacecraft has entered it. No instrument has sampled its chemistry directly. No sonar has mapped its floor. No thermometer has measured its waters. Everything we know comes from careful inference, from clues scattered across a world billions of kilometers away. Yet the conclusion remains remarkably persuasive. The ocean is there. Perhaps the most striking aspect is its persistence. Many discoveries impress us because they are dramatic. Explosions, collisions, eruptions, and sudden transformations capture attention. Pluto's ocean tells a different story. Its achievement is endurance. It survived through the formation of planets, through mass extinctions, through the rise and fall of species, through every empire, every language, every story humanity has ever created. Still, it remains. But there is another reason this discovery lingers in the mind. The ocean challenges something deeper than a scientific assumption. It challenges intuition. We expected warmth near stars. We expected activity near giant planets. We expected distant icy worlds to be frozen through and inert. Instead, we found liquid water at the edge of the solar system. The fact feels larger than the world itself. When you look into the night sky, after knowing this, the darkness no longer appears empty. Hidden beneath countless frozen surfaces may be environments we have never imagined, carrying histories older than our species, and perhaps older than life on Earth itself. And beneath Pluto, one such ocean waits. Alone in the darkness, at the edge of the solar system, waiting for nothing. Water appears in many forms across our solar system. Sometimes it falls from clouds. Sometimes it freezes into glaciers. Sometimes it drifts through space as vapor. Yet beneath these different expressions lies a common thread, one that stretches from the inner planets to the most distant frontier we have explored. Water endures. On Venus, traces of an ancient past hint at a world that may once have possessed far greater quantities than it does today. Earth followed a different path. Here, water gathered into oceans, sculpted coastlines, transported minerals, moderated climate, and became the environment in which every known living thing emerged. The story continued outward. Mars preserves dry river valleys, delta formations, and lake basins carved more than 3 billion years ago. Though its surface is colder now, vast reserves remain locked beneath dust and stone. Far beyond Mars, Europa carries a global ocean beneath an icy shell. Fractures open across its surface. Material rises. The interior remains active. Enceladus revealed something even more remarkable. Jets of water burst through fractures near its south pole, carrying salts, organic compounds, and molecular hydrogen into space. Those plumes transformed our understanding of where liquid water could survive. They showed that even small icy worlds could maintain hidden oceans for immense spans of time. But the journey eventually led farther still, past Jupiter, past Saturn, past Neptune. There, at the edge of the planetary realm, we encountered Pluto. Everything about it seemed to argue against complexity. Its small size suggested rapid cooling. Its great distance from the sun implied deep freezing. For generations, it appeared to be a relic preserved in cosmic cold. The evidence told another story. Beneath Sputnik Planitia and the surrounding crust, liquid water likely survives under tens of kilometers of ice. Radioactive elements within Pluto's rocky interior release heat through gradual decay. Methane clathrates, crystalline structures that trap gas molecules within water ice, provide insulation. Together, they have preserved an ocean for nearly the entire age of the solar system. An extraordinary outcome. The farther we traveled from the sun, the broader the lesson became. Water does not disappear as easily as we once imagined. Given the right conditions, it adapts, it hides, it persists beneath rock, beneath ice, beneath atmospheres, and sometimes beneath worlds we nearly overlooked. Pluto became the clearest expression of that truth. We underestimated it repeatedly. We thought it was too small to remain active. We thought it was too distant to matter. We assumed it belonged among the frozen remnants of planetary formation. Instead, it revealed geological activity, atmospheric cycles, and a buried ocean older than complex life on Earth. And somewhere beneath the bright plains of Tomba Regio, at this very moment, liquid water still exists. No human has seen it, no machine has touched it. Yet it remains there, held between cold above and warmth below, continuing a history 4.5 billion years long. Perhaps that is the final lesson Pluto offers. Worlds change, definitions change, scientific models change. Water persists. And in the darkness beyond Neptune, where sunlight arrives only as a distant spark, an unseen ocean continues its patient existence, asking nothing, proving nothing, simply enduring through time itself.